Okay, so today we will discuss the first section of the same paper, which is the introduction part. So it says that the surveillance systems pose specific requirements on the camera calibration, and the cameras are typically placed in hardly accessible locations. So that's like one of the limitation in the current camera calibration situation. The camera is somewhere which is not easily accessible, and the optics are focused at longer distances. So the common pattern based calibration approaches, so these are the common approaches. Pattern based calibration approaches, they are not usable anymore, and that's why there are many solutions to place the markers to the observed scene. These are other methods of calibration, the manual ones. So you place the markers to the observed scene, or you measure the existing geometric features. Now, the problem with this kind of manual calibration approach is that the approaches are laborious, takes a lot of labor, and they are also inconvenient. Inconvenient in terms of the camera setup, like you have to manually click on the measured features in the image, and also in terms of the fact that you have to physically visit the scene and measure the distances. So these are the problems that are associated with the calibration approaches, the manual. So in this paper, the focus is on precise and fully automatic traffic surveillance camera calibration plus the scene scale for proper speed measurement. So the most important point here is fully automatic. It has to be precise and it has to be fully automatic. The method which is proposed for the speed measurement here, it deals with significant viewpoint variations. So it should work for different viewpoints, it should work for different zoom factors and other roads and densities of traffic, different types of roads. These are the problems that should be covered with this method. Also, if the method is to be applicable for large scale deployment, if you have to do the speed detection for on a large scale, the system should be self-sufficient. It should be able to run fully automatically without the need to stop the traffic for installation or for the calibration purposes. So all in all, the previous methods which are not automatic, they have certain limitations because of the approaches being laborious and inconvenient for the setup of camera, and the fact that you have to physically visit the scene and measure the distances. So there is a need to have a precise and fully automatic camera calibration method, especially if you want to deploy on a large scale. And the method should be able to cover all the viewpoints, zoom factors, various types of road, and densities of traffic. The solution which is presented here uses the method for camera calibration by making use of two detected vanishing points. So you have two detected vanishing points, and the work is built upon previous work by Dubska in 14 and 15. But this calibration procedure allows for reconstruction of the rotation metrics and intrinsic parameters from the vanishing points. So you reconstruct the rotation matrix from this method and you get the intrinsic parameters from the vanishing points. But it is still necessary to have the scene scale. The scene scale is the important part. The detection is done by faster RCNN, and then the detected vehicles are classified using fine-grained classification CNN method, and bounding boxes of 3D models are used to align the detected vehicles. This method of calibration, which makes use of the vanishing point, it allows for full reconstruction of the viewpoint of the vehicle. So you're able to understand the entire viewpoint of the vehicle. You're able to reconstruct that using the vanishing point based calibration. And in this part, the only free parameter is the scene scale. So there's a figure that shows the 3D model and aligned images. This figure, we can go over that in later sections. So this project, the results from this project were that this method, which is presented in this paper, outperforms the existing automatic camera calibration method by Dubska in 2014. So it does outperform that method, and the calibration which is obtained from the manual measurements on the road as well. And this is important because in the previous approaches, this was a major point that previously automation always compromised accuracy, so there was always a trade-off. But this paper presented work that shows that fully automatic calibration methods can produce better results than the manual calibration. The existing solutions for traffic surveillance camera calibrations, all these are papers associated to that. They usually have limitations for real world applications. So whatever solutions existed up till 2016, I would say, there were limitations for the real world applications. And what kind of limitations were there? It was due to some viewpoints or probably some manual work for camera. So there's only one work which was by Dubska in 14 which did not have these limitations, and so the paper has been compared with this. There's a comprehensive review in a recent dataset paper, which is the Brno Comp Speed by Sokor as well. Alright, so the key contributions of this paper are the highlights of this paper. So you're supposed to get an improved camera calibration method by detecting 2 vanishing points. The error is reduced by 50%, so that's important. There's a method for scene scale inference which definitely outperforms the automatic traffic camera calibration methods and the other manual calibrations for the measurement of speed using a monocular camera. So the first was camera calibration method, then a method for scene scale inference, and the last is that the results show that when used for speed measurement task, the automatic method, can perform better than the laborious manual calibration, which is more accurate and treated as the ground truth. So that's also an important finding. So in the next section, we'll be looking at previous work, all the related work for this